you. So our next speaker is Vaibhav Gadre from Glasgow, and the title of his talk is Cusp, Excursions of Random Geodesics for Weil Petersson Teichmüller.
I want to thank the organizers for inviting me. This talk is going to be exercise in evasion, really. I mean, I'm going to try to be as simple as possible. In general, when you're talking about Weil Petersson metric, things get technical and complicated. I want to try to avoid that as much as I can. Okay, so I'm going to first define Weil Petersson type metrics and surfaces. So what is the picture? The picture is we have a surface with some number of mark points, which I'll call Pi. So the definition of a WP type metric is going to be, it's a Riemannian metric, so DWP is an incomplete Riemannian metric. Okay, I should say negatively curved Riemannian metric on S minus this list of points such that the completion is S and in the Cusp neighborhood the metric is asymptotically to a metric on a surface of revolution of the curve. Look like that. This is a surface of revolution of y is equal to x to the power r to the j for rj bigger than 2. So at near each cusp, this neighborhoods that I've shown, at each of these neighborhoods, the metric asymptotically looks like a metric on the surface of revolution. Okay, so and I could be more technical here, but I will not. That's good enough for this talk. And now you can notice that, for example, just because of the cuspidal structure, this metric is incomplete because I could just hit the cusp in finite time. So
you put the induced Euclidean metric on this thing which is negatively curved.
Yeah, you take the metric induced on this from R3. Right.
So what's Rj for the actual modular curve?
3.
Not 3 times. The third.
No. No.
Q. Oh, it is? Okay.
Yes. Y is equal to x cubed. All right. Any more questions? Okay, so notice the following. So in this setup, maybe I need one more thing. I want different color. If I have a point, and I'm really interested in points in the cusp neighborhood, if I have a point, I could take the distance of the point from the cusp. So the distance, this distance here, I'm going to call delta j. Can everyone see this? The distance from the jth cusp. Okay, so there is a Liouville measure for the flow, WP. So this is the Liouville measure. So I first need to explain why there is a flow. So there are certainly geodesics that crash into these cusp points in finite time, but that's a measure zero set. So on a full measure set, you can keep going on forever. So that gives you a flow on the surface. So this measure really, you should think of it as a measure on the unit tangent bundle of S. Okay, so having set that up, let me immediately state the theorem. So this is joint work with Carlos Matheus. So the theorem says that there exists C bigger than 1 such that for all epsilon bigger than 0, mu WP almost every geodesic phi t of V, or I'm going to sample V from T1 of S, and then I'm going to take the geodesic that V determines. So that's my notation for the geodesic ray starting with V. So this geodesic satisfies the following bounds. It satisfies 1 over C to the T to the 1 plus epsilon over Rj less than or equal to infimum T less than T of the delta J, the distance to the cusp, phi T of V is less than C over T minus 1 minus epsilon over 2Rj. So basically what I'm saying here for all T larger than. So what we're analyzing is, imagine you take the random geodesic. Now that's defined, it's defined for all times, and then it will sort of wander into this cusp neighborhood, spend some time here, wander back out, wander back in, wander back out, and we want to know how close does it get to the cusp. And the closest it gets is within these bounds. So that it definitely gets this close, and it gets at most that close. Okay? So that's the theorem. Okay, so what's the motivation for studying WP types metrics on surfaces? So here is an example. The motivation really comes from moduli spaces of Riemann surfaces. So this gadget is Teichmüller space of a surface on the same surface, let me call it X, or modded out by the mapping cluster. And this the moduli space has its own Weil Petersson metric. So there is a DWP, which is a Weil Petersson metric. On M, and it has its own Liouville measure. So as an example, if I were to consider the punctured torus, so we have M, which is SL to Z, the quotient of H2 by SL to Z, then on this moduli space we have a Weil Petersson metric, and by Wolpert's result, the area formed in the Weil Petersson metric looks like dl wedge d tau, but these are the Fenchel-Nielsen coordinates on the modular surface. So here, now you can just do a calculation which looks like the length of a curve. So if I take the upper half space model, and this will get back to guys' question. So if I have an upper half space model, and if I have a point x, y in the upper half space, then the length. So this is some marked torus, and the length of the curves will satisfy. Will have leading term that looks like 1 over y. Some curve is getting short, and you go into the cusp neighborhood. The length looks like 1 over y, and the twist parameter looks like x over y. So those are the leading terms, and then if you do the calculation, then dl is about it's 1 over y dy, 1 over y squared dy, and d tau, the lead, well, d tau looks like x over y dx. And then you take the wedge, you see that you get y cubed. So once you see y cubed, you also see that, for example, if I take a path that goes straight off to infinity, you take a path from a point that goes straight off to infinity, now your x is fixed, and we are integrating 1 over y squared dy, 1 over y squared dy going up. Okay? And that's
1 over y to the 3 halves, right?
1 over y to the 3 halves, yeah. Take the root of whatever. Yeah. And then that has finite limit. So you're crashing into infinity in finite time. This doesn't happen in the hyperbolic method, for example. Okay. So now we have this result which is like the toy version of what you want to do. So what's the result for moduli spaces in general? The result for moduli spaces in general has a conditional, it's a conditional result. So the results for moduli spaces is the following. So there are two parts to this. Again, it's joint work with Matheus. So for mu, WP almost every quadratic differential Q in the cotangent bundle of M, and for any kappa bigger than 0, we have that the system along phi t of V of Q is bigger than t to the minus 1 over 3 minus kappa for some t less than capital T, and for all t large enough.
I'm sorry, are you in the puncture torus?
No, this is not, this is the general result.
The general, this is the general.
This is true without any mixing assumptions.
Okay.
So this is, I mean, these are a class of results which are shrinking target results. If you're shrinking the target fast enough, then you get bounds that you cannot hit the target infinitely often. So these kind of bounds sort of come one way, the bounds sort of come without any mixing assumptions. The second part of the theorem will require mixing. So the system here is the hyperbolic system. This is a sequence of marked hyperbolic surfaces. You can record the system and record its hyperbolic length. So length. So this should be length of the system. Of shortest. Okay.
So, sorry, what is this? This says no matter where you start, you always,
For almost every geodesic, you will always satisfy.
at some
Yeah.
time, there
Yeah.
will be a curve that isn't too short.
Yes. Not sometimes. If you aggregate over all times, you cannot be. You have to have at least gone at least that deep. These targets are not shrinking fast enough, so you keep hitting them infinitely often.
Yeah, but for some time.
For some time, yes. Of course, you'll go close to the cusp and come back out, and go close again and come back out, and this is sort of aggregated. So maybe I'm missing.
I think,
Yeah. This is correct, the way it's stated. This is the smallest system up to time t that you will see.
You mean cis VT of Q is the shortest for all time up to capital T, that's what you're saying?
No. This is a marked hyperbolic surface. Let's call that xt. I look at its system. For each t that is a marked hyperbolic surface xt, I look at its system. I record its length, and then there will be some time such that all of the systems up to that time will exceed this amount. You cannot get too close to the cusp.
You can say that capital T is large enough.
Yes, of course we do. Okay. I'm going to not write everything on the book. How large the capital T you need will depend on the Q question.
So I'm still kind of this is saying when capital T is large, for some time up to that time, the systole will be bigger than this number. For some,
No, sorry. Oh, yeah, sorry. For all.
oh, for all, okay, okay.
So much more interesting.
Yeah. Okay,
Sorry.
okay.
Typo.
Okay.
And the second part of the theorem, yes. Now the second part of the theorem requires a mixing assumption. So assuming WP flow on M is T to the minus C mixing for some C bigger than 0, we'll get that for almost every Q in T1 of M, and for any kappa bigger than 0, the system of phi t of Q, this will be at most e to the power minus minimum of 1 comma c over 8 minus kappa for some t again. So now here is some all. So this is bounds going both ways, but it requires a mixing assumption. I'll get back to the issues of mixing of the WP flow in a second. Okay. So why are these such problems interesting? So now I want to be really low tech, and I want to explain why such problems are interesting by actually not talking about WP at all. So as a second part of the talk, I want to make the case for studying problems like this. So the only reason, one of the reasons we study problems like this is because several smart people prefer to study. So here are these smart people who are studying. So instead of the WP metric on a surface, if I take the hyperbolic metric, or you could take the Teichmüller metric on Mg. There are the logarithm laws. So Sullivan in the first case and Maser in the second case say the following. So random geodesics satisfy the limit suit t going to infinity of the distance in M or S, I'm going to put M here directly, between the initial point and the point after time t over log t, this is equal to 1/2. Okay? So these are the logarithm laws. So the picture is now we have actual cusps on a surface or in Mg, and our geodesic sort of wanders into the cusp neighborhood, goes certain depth deep, comes back out, and you want to measure what is the deepest that it gets to up to time t. And in fact, there's a limiting law that you can do. Right? It has log t depth in the thin part. Okay, and again for all t large. This is okay. This is a limit statement. This is nicer to say. Okay, one more thing I should say. There are higher ranked versions of this. You can climb up and not do this. So these are again log laws for diagonal flow. And now I'm actually going to talk about the log laws first to give you an idea of how I would approach questions like this for WP method. Okay, so here is a simplistic, here is a simple heuristic I wanted to give to explain the log law. So I want to draw a picture in the upper half plane.
Is this one half morally the sort of square root excursions and Brownian motion? Is it the same one half?
Brownian motions in the plane.
Yeah, I mean, this is hyperbolic, but still, there's, I vaguely remember Sullivan mumbling something about going on. It certainly doesn't get,
Brownian motion in the hyperbolic plane diverges. In
Well,
fact,
okay,
has
then.
linear drift. So I'm not sure.
okay, so the Euclidean thing has nothing to do.
Yeah, I'm not really sure. Yeah, I'm not sure of the answer to that. And
Maybe when you're in the cusp, something else dominates. There's a random.
but this is a constant curvature metric. The metric, I mean the cusp. I mean, it's really some question of, you can think of exhausting your cusp by, take a system of neighborhoods exhausting the cusp. It's really a question of whether the flow is strong enough to hit as you shrink your target. So it's really a shrinking target kind of question. I don't think it's the same one half actually. Okay, so here is the upper half space model. And now we really should keep like the modular surface in mind when this discussion happens. So let me draw the cusp neighborhood. The cusp neighborhood I'm going to take. This is imaginary part of Z, bigger than or equal to 1. And up here, I'm going to take a strip. So let's draw a strip up here, which is between R over 2 and R. So this is imaginary part Z, R over 2. And I want to look at this strip. So if I call this strip as SR, its projection downstairs, you can project SR to, so now I can simply think of my surface as given by a lattice in non-uniform lattice in SL to R. So my surface is exhibited as gamma mod H2, let's call this X. And XR will be the projection of SR into this. So this is SR upstairs projecting to XR in. Okay? So the picture is we have what does the fundamental domain look like when it intersects the cusp part? It just looks like a bunch of vertical strips. Right?
And so in this X is supposed to have a cusp at it directly at infinity, that's sort of.
Yeah. This is a lift of, I mean, there will be other hormones.
Right,
This is a lift of a particular cusp. Okay, and now we imagine that we actually have a geodesic that crosses this strip. So it does an excursion which is depth at least 1/2 log of R. Okay, so let's draw that in some other color. Here's a geodesic. That, so now I'm talking about hyperbolic geodesic, but it does that. Okay. I imagine this was a random geodesic, so you could ask the question, well, how much time should I expect my random geodesic to spend in this strip? So I will take one more notation here. Fr is going to be the characteristic function of XR. So the time spent by a geodesic in the blue region is simply the integral up to time t of Fr. So the time spent in XR is simply the integral from 0 to t of Fr of phi t of t. Okay. So random geodesic, what should the estimate be for this? This should be, I'll put here, I'll put this equality in boxes of various colors because that's the main point. T times T, the volume of XR. So this is T times the volume of XR. And we can do this calculation using the standard hyperbolic metric it looks like dx dy over y square. So we integrate this over a patch of the fundamental domain, and we can find its volume. This is about 1 over r. Okay? That's the volume of the blue region inside on my portion. Okay. So that's the time spent in XR. So now let's set a we'll set t first. Sorry, set r first to be equal to t to the power a, where a is bigger than 1. Then the time spent is equal to t 1 minus a, which goes to 0 as t goes to infinity. Alright, but any geodesic that crosses the blue region has to spend time at least 1/2 log 2 in the blue region. That's just basic hyperbolic geometry. The length of this segment here is at least 1/2 log 2. So if the time goes to 0, that means that our setup does not allow an excursion of that size. Okay? So this goes to 0, which means that for large times, no excursion is possible. Right? So now, again, if you set r the other way, where a is less than 1, then time spent is actually quite large. So it's 1 minus a, which goes to infinity as t goes to infinity. So which means we'll definitely see an excursion of this size. Now our imaginary part, r, was about t to the a, for any a, choice of a. So if you take half log t to the a, which will get exactly 1/2 a times log t, and a was any constant bigger than 1, so you see this will have to come out. Okay? Right, the depth of that geodesic is at least, so this is at least 1/2 times log of a log of r, which is, well, essentially r over 1, so it's which is equal to 1/2 of log of t to the a, so it's a over 2 log t. A was any constant, I can take a closer and closer to 1, you get 1/2 log t. Okay? So it's a very simple heuristic of how the log law should be explained. So simple. I put this equality sign in a big box, which is supposed to have all sorts of colors to raise your eyebrows. So what's going on? Why isn't this heuristic just an easy proof? The problem is that I have here assumed that my time average converges to the space average at time 0, well, essentially really fast. So if I could get a rate in this equality, I could promote this argument to a proof. Okay, so that's the next part of the talk, which is how do you promote So this arrow, this equality here needs the following care. So if you have a flow which is mixing, there is some hope. So the next part of the idea is mixing of flow is to be used to get effective convergence of ergodic averages. Once I can do that, then there is, you kind of just estimate the rate that you get in this convergence, and then you use that to produce bounds. And in fact, this will actually produce refinements of the log power set going this way. So one subtle point here. What is the subtle point? The subtle point here is that notice that this convergence, the rate of convergence is not applied to a function which is sitting ahead of time. This is applied to a time-dependent function. So the subtle point is that I'm trying to do effective ergodic theory on time-dependent function. And this is where we need that assumption of mixing. Anyway, all right. So, you know, if you are a rubbish mathematician like me, you have one good idea and you milk it forever. So, if you take this idea of using effective ergodic theory in this way, there are several.
Sorry, where's the time dependence function here?
Because this R was set to be t to the a,
Oh, I
and this
see.
strip is sort of moving
Oh, I
up
see.
into the cusp as you go along.
Okay.
All right. So here are the various contexts where you can make this idea to give you something useful. So first is, so I should say, by the way, this one more thing I should say. If you have some, you know, there are all of these are related to Diophantine approximation, questions, approximations, Kinchin theorem, etc. So I just for a punchline, I will actually give you the continued fraction versions of all of these statements just as a punchline. Okay, so here it's like the largest coefficient up to, if you had a continued fraction expansion, a random continued fraction expansion, the largest coefficient up to, take the first n coefficients, look at the largest one, that has size about log n. All right. So applications of force. So again, these laws were taking the maximum coefficients, the maximum excursions. But the same ideas could be used to compute average excursions as well. So there was a maximal excursion, these bounds were for maximal ones, but there is nothing stopping from using this setup to do more. So you could talk about average excursions. Anyway, so applications. So the first one, so average excursion, in this context, average excursion is unbounded. This is the same as the statement that the maximum coefficient, so if I take the following sum, a1 plus an over n, this goes to infinity along the random continuous fraction. But you could then try to finesse this and ask yourself, well, what happens, what should be the growth rate of the numerator? So you could guess, well, maybe it's n log n. But even with n log n, you only get a weak log. It says that the measure of the set, I'm not going to state this statement, but basically it says that the measure of the set where this sum divided by n log n differs from the expected thing by epsilon, this deviation is epsilon, then the measure of the set goes to 0. I actually did say. And then there is a trim sum strong law, which says that mu of, so which says that if you take the sum and you remove the largest coefficient over n log n, then that actually converges. This is almost every state. So it turns out that all of this generalizes, and you get a trim sum law for Teichmüller geodesics on SL2R orbit fluids. And in fact, the right hand side, the limit of this trim sum log law turns out to be something called Segal-Rich constant. Anyway, so this relates the dynamics of the Teichmüller flow directly to the orbit fluid. Second application, maybe on a different board. second thing to do here would be, so this was flat surfaces, in the world of flat surfaces. You could apply this idea to flat surfaces to get results like that. You could apply it to random walks on the mapping class group to get bounds on, the result is bounds on maximal excursions of, it's a different notion of random, but random geodesics. This is work in progress with Joseph Ma. And finally, you are using this idea to get the bounds in the WP method. So what we need is the information about mixing of the two. So the final thing I want to say here is, if you took the Weil Petersson metric on where WP type metrics on surfaces, so the flow is ergodic. It is ergodic. This is a result of polygon Weiss. This marker. It's exponentially mixing. This is a result of Burns. Can I just, I'll move that way, see how it means now. Burns, Matheus, Maser, Matheus, Wilkinson. And in the general case for moduli spaces, the WP flow is ergodic. Again, a different paper of, no, this is Burns, Maser, and Wilkinson. And at most polynomially mixing, this Burns, Matheus, Maser, Matheus, Wilkinson. As a different paper, maybe 2 items. So now the ergodic machinery is there, and then that helps us to get started to study problems like this. Here are some quirks that you notice about the WP metric. I'll just explain it in terms of what you see for surfaces, WP type metrics and surfaces. So it's often repeated that it's very easy to do excursions in WP metric, which is it is because it's very easy to wind around the cusp. But at the same time, the cusp has much smaller volume. The decay rate of volumes of the cusp are much faster. So what wins? Is it easy to wind around or not? What wins? So the point is that we had this picture where in the upper half place, our hyperbolic metric looks like dx dy over y square. The WP metric looks like dx dy over y cube. And because of this, the curvature is actually blowing up to minus infinity. Because of this, the vertical direction that heads straight to the cusp is quite unstable, right? Because of the type of metric it is. So in fact, a small perturbation from that produces a shallower excursion in WP than it does in hyperbolic. So as a result, what happens is that the maximal excursion for WP is actually shallower than the maximal excursion. Okay, you have to set up a proper comparison here, but shallower than for the maximal excursion for hyperbolic. Which came as a surprise to me when I first, because it's sort of, that's sort of easy to wind around in WP, but it's actually smaller. And in fact, you can compute, and you have to be a little bit careful about setting up the comparison. The time parameter along the WP geodesic is different from a time parameter along the hyperbolic geodesic. Look, all of these estimates were measuring times in their own setups. So you need to know, for example, to set up a comparison that as you take the time parameter along the WP path, your hyperbolic distance, how does it grow? And in fact, it turns out that it goes linearly so the time change is linear in this setup. Okay, you could also ask, well, what is the average coefficient look like? So we are in the modular surface. We have our WP path, and we could try to compute the sum of the winding numbers around the cusp. You go to the cusp, as you do an excursion, you wind some number of times around the cusp, come back out, you wind some more, and so on. And you could ask, what is the average winding number? And in this case, for WP, the average winding number is actually finite. Whereas here, as I mentioned here, for example here, it's infinite. So it's sort of interesting to see what's going on.
That's in the, like any of your surfaces?
Yeah, any of my surfaces, you do this computation of winding number around. Take the total winding number around the cusps and calculate that. That grows linearly in time, which does not grow, for example, for the hyperbolic metric. And it does not grow linearly in the Teichmüller metric on modulus. So these metrics are kind of, the asymptotics are completely different from what you see in the Teichmüller setting. But however, I mean, it's still, yeah. So for example, you could ask, well, along the random WP geodesic, the reason we are studying these winding numbers is because eventually we want to study subsurface projections. How the subsurface projections grow along the random geodesic, and then maybe you can say things like the ending lamination associated to a random WP geodesic is uniquely ergodic. Actually, this should be true from a paper of Ursula's, which sets up a conjugacy between the WP flow and the Teichmüller flow. But
So
more explicit.
Here the average is going to infinity for
this is hyperbolic.
hyperbolic, and here the average is
It's bounded. All right, I'll stop here.
Any questions?
So
Yeah.
what can you say about the max excursion in the random walk setting?
Yes. It's about log.
Are these finitely supported measures?
Don't have to be finite
Does-
first moment with respect to
Just for that first one.
Actually, hang on a second. It's a paper being written, so you're. Definitely for finitely supported measures. Finite first moment, I'm a little worried there are some effective versions that we need. So don't put me on that. I'm big film, so definitely don't put me on that.
More questions? There's not this thing.